Hi, everyone. I'm Joey Cruz, and this is our solar plus storage proposal presentation for Miami University. At App Solar, we take pride in our multidisciplinary approach. Our team is a mix of undergraduate and graduate students representing 6 different programs, ensuring that your project's goals are completed by taking into account a variety of different perspectives. Our presenters today are going to be Ransom Cope, James Poole, Finley Collins, Duncan Burns, and myself.
So we have designed our systems in accordance with the university's 2040 Climate Action Plan, and our proposal aids the university in achieving carbon neutrality at the lowest possible cost by shaving peak demand and reducing energy costs with a solar plus storage system, all while diversifying the university's renewable energy portfolio. In terms of site restrictions and development considerations, we elected to develop both a ground mount and a ballasted system due to the lack of south-facing roofs, the historic nature of many of the campus buildings, and the increased difficulties of installation and interconnection that rooftop systems would have created. Natural gas generator use has been replaced with a solar plus storage system covering 100% of the load, providing diverse and equitable infrastructure. Furthermore, we explored all options for system design, resulting in the most cost-effective solution while seamlessly aligning with the university's climate goals. And I'm going to hand it off to Ransom to cover the development plan.
Thank you, Finley. Good afternoon, everyone. We confirm that Miami University is the authority having jurisdiction over the district using the City of Oxford's interactive zoning viewer. The area is zoned MU, or University District, which allows for development that facilitates and supports the work of the university. Overlaying the area is the Western Historic District, which is a protected historic area designated by the Historic and Architectural Preservation Commission of the City of Oxford. The HAPC lays out design requirements for making alterations or upgrades to the historically protected buildings. And while these requirements are not directly applicable to our systems, we will allow for adequate time to work closely with the HAPC to minimize the impact of the historic nature of the area. There are a number of applicable ordinances and regulations that apply to the project, covering all areas from construction documents, inspections, and permits to engineering requirements, setbacks, and environmental regulations. All development will be in compliance with the applicable codes and ordinances. We used a number of cross-cutting remote analysis methods in order to select the most optimal sites, and we see few obstacles in the development of the chosen sites. A thorough site inspection and analysis is recommended to confirm our preliminary findings. In addition, there are several permits that apply to the development of this project that we have allocated up to 5 months to procure. However, we are very confident that this process will be much quicker. We have designed and planned a very conservative 18-month phased construction timeline for the project, and as stated earlier, we expect the process to move much faster. Some considerations of the extended timeline are fluctuations in the supply chain and tariffs imposed on imported panels. We will begin material procurement, including securing and storing panels early in the development process to negate these issues. Oxford has the highest poverty rate of college towns in Ohio, making the overall equity of the project of the utmost importance. This was taken into consideration at every stage of the project, from local workforce involvement to minimizing environmental impact on the community. I'm going to hand it over to Joey, Finley, and James to talk about system design.
We designed 3 PV systems, a ground mount system to the south, a ballasted system on the geothermal well field, and a student engagement array. The estimated total annual production is over 7.5 gigawatt hours, producing over 100% renewable energy to the buildings in our district use case without exporting excess energy to the grid. We designed 4 battery storage systems to meet the university's peak load shaving needs and resiliency goals. The size of our PV systems were determined by designating the university's critical loads, which is a combination of the 15-minute load data from each of the 18 buildings. This was used to ensure that the buildings within the provided district would be 100% powered by renewable energy while also not exceeding the university's baseload capacity of 7 megawatts. Also, when designing any solar plus storage system, it is important to account for any determined critical loads. Miami U wanted their solar plus storage system to assist in shaving peak demand and provide power in times of outages. More specifically, keeping the geothermal energy plant operating during a 2-hour outage during the highest load. This resulted in a critical load calculation consisting of a combination of the university's estimated peak demand values and the entire load of the geothermal energy plant. We also ensured that the system would survive the 4 highest peaks of the geothermal energy plant's load and peak demand simultaneously, allowing for additional loads to be served by the batteries in case of an outage. During an outage, the geothermal battery will typically be able to serve additional loads, as it is going to have ample capacity. In fact, the dedicated geothermal plant battery is large enough to power the average load of the geothermal plant for almost 6 hours. The PV systems were sized by the estimated annual production that REOPT calculated, not the capacity of the system that was recommended. We found the production results from SAM to be more accurate. However, we did find the REOPT battery sizing to be sufficient.
For our module selection, we have chosen the Canadian Solar 700-watt bifacial panel. And this panel allows for over 4.5% increased efficiency through its bifaciality. By using a 700-watt panel over your standard 450-watt panel, we have increased system rated capacity by 26.4%. And for our inverters, we chose the Huawei 100 kilowatt string inverters for their unmatched efficiency, interconnection flexibility, and their safety features. The geothermal ballast array is located on the geothermal energy plant well field, which poses certain design restrictions such as requiring a ballasted mounting. However, this allows us to achieve zero shading relatively easily. We chose a single axis tracking mount with a reflective coating designed to reflect light into the back of the panel, further enhancing the bifacial capabilities of this system. This array has a nameplate capacity of 2.6 megawatts with an estimated annual energy production of just under 4 gigawatt hours. For a ground mount array with less restrictive design characteristics, we chose a standard single axis tracking ground mount. Also with zero shading, this array has a nameplate capacity of 2.4 megawatts with an annual energy production of 3.5 megawatt hours. And finally, the Miamia array is projected to be an 8 kilowatt system showcasing the Miamia Heritage logo. This logo serves as a symbol of unity, cooperation, and respect between Miami U and the Miamia tribe, while exemplifying the dedication to sustainability and the environment outlined in the Climate Action Plan. This array was based on the Appalachian State University Mountain Array, which you can see over to the left. And from our experience, this array's social impact on campus is priceless.
Our battery system is composed of 4 separate battery banks. Using multiple battery banks increases resilience and modularity for future projects the university might take. The first and largest battery bank was designed for the sole purpose of supporting the geothermal energy plant in a blackout scenario, and the 3 additional battery banks are primarily used for peak load shaving, but they can also provide emergency support power for the geothermal plant if needed. We chose lithium cobalt oxide batteries because they have a very high energy density, high safety standards, a large temperature range, and are the cheapest chemistry of the batteries we analyzed and compared. We used the System Advisor model to model and estimate PV production and the REOPT tool for battery and solar dispatch in the context of the university's loads. And as shown by the graph in the right-hand corner, our modeled PV system seamlessly powers the university's loads holistically and cost-effectively. And I'm going to hand this off to Joey and Duncan for our distribution information.
Miami University is located in a competitive utility market within the PGM Regional Transmission Organization footprint. In this market, only part of the cost that makes up the electric bill is directly related to the amount of energy consumed. The other costs are related to the impact that the university has on the grid, like maintenance of transmission infrastructure and reserve capacity needed to meet demand. The proportion of these impact costs that Miami U is accountable for is based on how much they contribute to the overall power consumption during the RTO's peak loading event. The university currently mitigates their impact on the transmission infrastructure and the peak demand costs they are liable for by generating power from 2 5.5 megawatt natural gas generators on days when the utilities expect high grid demand. Unfortunately, due to the slow dispatch time of these generators, the university is financially incentivized to run their generators at maximum capacity for the full day, and this leads to high fuel costs and a massive increase in the campus's Scope 1 emissions. Looking at the graph on the right, you can see how the current natural gas generator solution is sluggish and inefficient. In comparison, our solar plus storage system is capable of near instantaneous dispatch to efficiently shape peak demand. Having improved control of the demand will allow Miami U the option to operate in a real-time peak demand rate structure, previously only available to industrial customers that have this level of control over their load. The rapid response time of the system allows peak demand to be avoided efficiently and without any direct emissions. This saves the university money and allows them to better achieve their climate goals. Our system can reduce the impact of the university on the main grid, but we also have to be aware of any impacts that our system could have on the university's distribution network. Distribution impact concerns of photovoltaic projects are due to their intermittent nature. These system impacts can be particularly tough to mitigate, as power generation, like the weather, can be difficult to forecast. As the majority of photovoltaic capacity is connected to low voltage distribution networks, projects can be hindered through issues related to voltage quality, including over voltage, imbalance, flicker, harmonics, and opacity. To address these issues, it is essential to have an understanding of the capacity available at each interconnection point.
Our innovative solar and storage systems are AC coupled, giving the university the freedom to add additional storage capacity or renewable energy expansion to help with the campus in their plans. For example, in Miami U's Climate Action Plan, they plan to electrify their fleet when cost effective or by 2040. With the advancements being made in vehicle grid EV charging, the proposed system has the infrastructure to support the bidirectional power flow between the campus and its electrified fleet. Retrofitting the charging infrastructure could show a quick return on investment for the university, expediting the fleet electrification process and giving the university 7 megawatt-hours of variable storage capacity.
Here we have some maps of our system interconnection points. And as shown in the table of the right, we wanted to ensure that each of the closest points of interconnection had sufficient PV hosting capacity. We utilized multiple interconnection points to avoid any excessive loading on any one part of the distribution network and in order to mitigate any issues related to voltage quality.
For distribution costs, our main considerations were interconnection costs and wire sizing. The inverters are placed at the end of the arrays to optimize future maintenance in space. This also minimizes the system's voltage drop and wiring costs because the wires used for PV stringing on the DC side are much smaller. As you can see by the table at the bottom right, these changes have minimal effects on the bottom line, but are still important considerations. Moving to the financials. We chose a target IRR of 8% to make our project enticing to investors. One of the barriers to financing renewable energy projects is the high initial investment or capital expenditures. We decided that debt equity would make a more accessible and enticing investment opportunity for merchant plant investors. Our PPA structure allows the investor to take advantage of a 40% investment tax credit and for the university to purchase energy at a lower rate. To address peak demand considerations effectively, a ratio was computed comparing the peak demand hour load profile to the total campus load profile. This ratio expresses a percentage of the total annual energy change, serves as the composite break-even point for the PPA rate. Any PPA rate below this calculated break-even rate will translate into net profit for the university, further optimizing financial returns.
Miami U's investment in its climate action plan, if done properly, can be profitable for all parties involved. This break-even PPA price shown in the previous slide was 4.7 cents per kilowatt hour. Our proposed PPA price of 3.8 cents per kilowatt hour creates a considerable return on investment for the investor while generating large savings for the university. Even with a conservative PPA escalation rate of 5%, the university can profit over $9 million over the 30-year life cycle of our project. As far as the investor is concerned, they can expect a 9% IRR with a debt equity of 40%. And now I'm going to let Duncan and Finley finish everything up.
This system will offset over 5,000 metric tons of CO2 annually, equivalent to taking 900 cars off the road or planting 100,000 trees.
All right, thank you, everybody. And on behalf of the App Solar team, we would like to extend a special thank you to Sarah Farrar and everyone at the National Renewable Energy Laboratory, along with the Department of Energy for putting on this competition. And we are ready to go for Q&A.